My name is Arsalan Farrukh and I teach physics and math. In this video, I will be going through some formulas of trigonometry and how to prove trigonometric identities. First of all, let's have a look at some of the formulas. You need to identify that if you have a right angle triangle, the side that's opposite to the angle that we are considering, we refer to that as perpendicular. And the side that's right next to the angle, that is called base. And the largest side, which is opposite to the 90-degree angle, is called hypotenuse. Now you need to learn these trigonometric ratios, which includes sine theta, which is perpendicular upon hypotenuse, cos theta, which is base over hypotenuse, and tan theta, which is equal to perpendicular upon base. Apart from that, there's another formula that relates the three sides of the triangle, that is called Pythagoras theorem, which means that hypotenuse square is equal to perpendicular square plus base square. Now let's look at what other formulas we can get out of here. First of all, we should know that the sum of three angles of a triangle is equal to 180 degrees. Since it is a right angle triangle, this angle is 90 degrees. So the sum of the remaining two angles must be 180. And if one of them is theta, the other one must be 90 minus theta. Now, if we look with the perspective of this particular angle and we find out the values of ratios, so if I have to find cos of 90 minus theta, this is the side that is adjacent to the angle. So adjacent over hypotenuse in this case is going to become perpendicular over hypotenuse. Similarly, if I'm trying to find out sine of 90 minus theta, so opposite over hypotenuse in this case becomes base over hypotenuse. Tan of 90 minus theta, then opposite over adjacent becomes base over perpendicular. Now, once we do identify these, that gives us some important formulas. If we look at it closely, that sine theta is perpendicular over hypotenuse and cos of 90 minus theta is also perpendicular over hypotenuse. So that means sine theta must be equal to cos of 90 minus theta. I get an identity from here. Similarly, if I look at cos theta, which was base over hypotenuse, but if I look at sine of 90 minus theta, that is also base over hypotenuse. So that means sine 90 minus theta must be equal to cos theta. Likewise, if I look at tan of 90 minus theta, that is base over perpendicular, whereas tan theta is perpendicular over base. That tells me that tan of 90 minus theta is 1 over tan theta. So these are the few formulas and the reason we've just come to know across, but somehow we have to learn these formulas. Moving on, if I have this Pythagoras theorem, which is perpendicular square plus base square equals hypotenuse square, I can divide the entire equation by hypotenuse square. So this becomes p square over h square, this becomes b square over h square, whereas h square over h square simplifies as 1. Now, if I will put the square on both the terms together, this can also be written down as p over h whole square. This can also be written down as b over h whole square. So p over h is sine theta and b over h is cos theta. So we can say that this equation can be written down as sine square theta plus cos square theta is identical to 1. And that gives us a very, very important formula to remember. Though it will be provided in the formula sheet, but we will be using this a lot. Now, if I look at sine theta, which is perpendicular over hypotenuse, and I look at cos theta, which is base over hypotenuse, and I divide these, I divide sine theta by cos theta, the hypotenuse will cancel out in both of them, and I will be left with perpendicular over base, which can be identified as tan theta. So that also tells me that tan theta is equal to sine theta over cos theta. So these are the two formulas that we will be using to try and prove different identities. Alongside that, you also need to memorize some standard values of trigonometric ratios. Like you need to know what is sine 30, you need to know what is sine 45, and so on and so forth. So for 0, 30, 45, 60, and 90, you have to learn the values of trigonometric ratios. So in some certain cases, examiner can give you a question where he says that give the exact value of sine 45. So you must know that that comes out to be 1 over root 2. Since we need to learn all of these values of trigonometric ratios, to learn these values, we can take two alternate approaches. To learn the values of 30-degree angle and 60-degree angle, we can consider an equilateral triangle, each side of which is equal to 2. And we drop a perpendicular from top vertex on the base, which also splits the base into two equal sides. So this is 1 and this is 1. Since it is an equilateral triangle, this angle must be 60 degrees. And since we have dropped a perpendicular right from this vertex, so that also splits the angle into two 30 degrees. Now, if we want to find out the trigonometric ratios, one more thing we need to do is to find out the length of this side. And we can find the length of this side by using the Pythagoras theorem. And once we do that, and we know that this side is root 3, we can find out all trigonometric ratios of 60 degrees and 30 degrees. Let's say I want to find out the trigonometric ratios of 60 degrees. Sine theta is perpendicular over hypotenuse, so sine 60 must be root 3 upon 2. Cos theta is base over hypotenuse, so for 60 degrees, cos theta would be 1 over 2. And tan theta is perpendicular over base, so for 60 degrees, it will be root 3 upon 1. Alternatively, we can also view it with the angle of 30 degrees. If you want to find out the ratios of 30 degrees angle, if you want to find sine 30, then perpendicular now becomes 1 and base is 2. So this is going to be sine 30, 1 over 2. Now, if you want to find out cos 30, the base will be root 3 and hypotenuse will be still 2, so that will be root 3 upon 2. And if we want to find out tan 30, that is perpendicular over base. So in this case, that is going to be 1 upon root 3. So that's how we can find out the trigonometric ratios for 60 degrees angle and 30 degrees angle. Similarly, if you want to find out the trigonometric ratios of 45 degree angles, what we can do is that we can consider an isosceles triangle whose vertical side and the horizontal side are both equal to 1. To find out its hypotenuse, I can apply Pythagoras theorem, which is under root 1 square plus 1 square, that simplifies to under root 2. Now I can find all trigonometric ratios for this one. Sine 45 is 1 over root 2. Cos 45 is base over hypotenuse, so that also becomes 1 over root 2. And then tan 45 is perpendicular over base, so that becomes 1 over 1. That's one way to look at it. There is another way. If you find this method a little long, what you can do is that you can start making this table. Just put in the values 0, 30, 45, 60, and 90, and sine ratio, cos ratio, and tan ratio. Now, you should write these numbers in order, which is 0, 1, 2, 3, and 4. Divide all of these numbers by 4 and take a square root of them. And that will give you all possible trigonometric ratios of sine theta. That is, sine 0 would be 0, sine 30 would be 1 over 2, sine 45 would be 1 over root 2, sine 60 would be root 3 upon 2, and sine 90 would be equal to 1. Now, once you have written all the trigonometric ratios, if you reverse their order, they become the trigonometric ratios of cos theta. So I write one that's written in the end, I write it in the beginning, then second last is written as second, and then you just keep on writing them in the reverse order and you will get the values of cos theta. As far as finding out the values of tan theta is concerned, you can use this ratio, this formula, to identify the ratios of tan theta. You divide 0 by 1, you get tan of 0. You divide half by root 3 by 2, that simplifies to 1 over root 3, that would be tan theta. Divide this by this, that simplifies to 1. Divide this by this, that simplifies to root 3. And as an identity, you must know that 1 over 0 is a very large value stated as infinity, which tells us that tan of 90 degrees is equal to infinity. Now moving on, we are going to try and see how to prove trigonometric identities, and before we head on, I really want you to make sure that you remember these two formulas, because we will be using these two formulas to prove all different trigonometric identities. Let's have a look at how we prove the identities. Like for example, I have to prove this is equal to this. First of all, you need to understand what is meant by identity, or in other words, what is different between a normal equation and an identity. Like for example, if you come across something like this, 2 sine square x minus sine x is equal to 5. So that's basically an equation. And there would be few values of x that will satisfy this equation. And later on in this chapter, you will also see that how these values are being determined. But there are some specific values which will satisfy this particular equation. What is different about identity is that they are identical. Means whatever value of x you're going to put in the left hand side, if you put the same value on the right hand side, you are going to get the same answer for every value. So equation is satisfied for specific values, but identities are satisfied for all possible values. When I have to prove an identity, I choose for a more complicated side that has more room for simplification, and I simplify it and I bring it to the equal to the other side. In most of the cases, your more complicated side would be the one on the left hand side, but obviously that is not the case always. You just have to pick the more complicated side, which I can see clearly. I can't work around a lot with cos x, but I can work around with this particular expression. So I'll start simplifying this. One thing is that you have a divisibility sign here, and then you have another divisibility sign here, and that gets a little confusing when you're trying to simplify this. And I would advise you to replace this sign of divisibility by this sign of divisibility. So your simplification would become comparatively easier. So 1 plus cos x is divided by 1 plus 1 over cos x. And then generally, whenever you're trying to prove a certain identity and you see that there's a possibility of simplifying it by taking LCM, please go for that. So in this case, I know that the denominator of 1 is 1, so I take the algebraic simplification of it, the LCM is cos x, and the numerator simplifies as cos x plus 1. If you find this thing slightly difficult, then you can just multiply cos x by 1 and then cos x plus 1 over cos x. This simplification is very much like a very basic algebraic simplification that you used to do earlier on, which would be like if you have to simplify 1 plus b upon a, you can also write it down as a upon a plus b upon a, and then a plus b upon a. So this is basically that kind of algebraic simplification. We're just doing it in terms of cos x. So this becomes cos x plus 1 divided by cos x. The advantage of writing down this divisibility sign is that whenever you get an opportunity, you can convert this into a multiplication sign by flipping this particular fraction. So if I write it as multiple, then cos x goes up and cos x plus 1 comes down. So if you look at that, and obviously it wouldn't make a difference if I write cos x plus 1 or 1 plus cos x, it is the same thing. It's just like if you add 2 plus 3 or 3 plus 2, you will get the same result. So 1 plus cos x and 1 plus cos x cancels out and you would be only left with cos x. And that is exactly what you have to prove over here. Once you start with one side and that simplifies to the other side, then that means that your identity has been proved. Let's move on to another example. We have 1 minus 2 sine square x, and we have to prove it to be equal to 2 cos square x minus 1. Starting with the left hand side, which is 1 minus 2 sine square x, I know that I don't want to have sine square here because I want to convert this into that form, and I don't want sine square. So I have to remove sine square and I have to bring in cos square. So I look back at the identities I have or the formulas I have, and I know that the formula that I can use directly is cos square x plus sine square x is equal to 1. Since I have to replace sine square x, so I can say that sine square x is equal to 1 minus cos square x. And once I do that, I can replace it by 1 minus cos square x. Now, this particular step was clearly driven by the fact that I have to bring it in terms of cos square, which is why sine square was replaced by cos square. So this becomes 1 minus cos square x, and then I just opened and simplified it. So it becomes 1 minus 2 plus 2 cos square x, and that becomes 2 cos square x minus 1. So that is equal to the right hand side, and that is the identity being proved. Let's have a look at another example. I have to prove 1 minus cos square x over 1 plus sine x equal to sine x. Clearly, I'm never going to start from this side because this is already the most simplified form and I won't be able to simplify it any further. So I start with the left hand side and I try and simplify this. So again, I am taking an LCM. One way to look at it is that this particular fraction is multiplied and divided by 1 plus sine x. So that's same, and then you can write down the numerator term, which is going to be 1 plus sine x minus cos square x. After writing this down, I can sort of rearrange it and sort of identify that 1 minus cos square x can be written out together, because since I will again recall that formula, which is sine square x plus cos square x is identical to 1, so I can replace 1 minus cos square x by shifting it to the other side by sine square x, and that's what I've done here. I've replaced 1 minus cos square x by sine square x. After doing that, you can do a bit of factorization here. You know that sine square x means there is sine x multiplying by sine x, and there's another sine x. So I can take sine x common and it will become sine x plus 1 or 1 plus sine x. That doesn't make a big difference. The reason I wrote it down as 1 plus sine x is because this becomes identical to this and I can cancel them out in numerator and denominator. And once I do that, I get my answer as sine x. The same thing that I did over here can also be done alternately by identifying that if cos square x I can replace directly here as 1 minus sine square x, then 1 minus sine square x can be looked as 1 square minus sine x square, sine x whole square. And we can use that formula of factorization here, which is a square minus b square is a minus b and a plus b. So 1 minus sine square x becomes 1 minus sine x into 1 plus sine x divided by 1 plus sine x, and 1 plus sine x and 1 plus sine x would cancel out. So this is 1 minus sine x being left over here. There's 1, so 1 and minus 1 minus sine x simplifies to 1 minus 1 plus sine x. That becomes sine x. Looking at another example, I would also advise you that whenever you have to try and prove a trigonometric identity, prefer to have the trigonometric ratios as sine and cos and not as tan. They are easier to simplify, which is why I can replace this tan x. Starting with the left hand side, I can replace this tan x as sine x over cos x, and I can replace this tan x as sine x over cos x as well. And 1 over sine x over cos x becomes cos x over sine x. It flips over, and this is still sine x over cos x over here. And then I'm going to take the LCM. One way to look at this simplification is that this goes and multiplies with this, and this goes and multiplies with this. So cos square x plus sine square x over sine x cos x. And then you will identify again that identity that we use every time, which is sine square x plus cos square x is equal to 1. So we can replace that by 1, and hence it becomes 1 over sine x cos x. Moving on with another example. This is also something very, very similar to what we did before. We don't want to have tan x here. Plus one more thing, I can see a lot of divisibility signs and that can easily confuse me. So I'm going to write that down as sine x, then this divisibility sign, and write down the entire denominator, replacing tan x by sine x over cos x. 1 over sine x over cos x becomes cos x over sine x. And then I can take LCM, 1 minus cos x over sine x Due to divisibility sign, I can flip it over. And then it becomes sine x into sine x, which can be simplified as sine square x upon 1 minus cos x. And 1 minus cos square x can be again factorized. By using the formula a square minus b square, it becomes a minus b and a plus b. And 1 minus cos x and 1 minus cos x would cancel out, and you would be only left with 1 plus cos x. That is what you had to prove in the beginning. And hence, this is also being proved. Similarly, I have been given another situation, and you must be identifying that in a lot of situations, factorization is a very, very good approach. So if I have to prove this identity, sine to the power 4x minus cos to the power 4x. And here I must clarify one thing, that if you have something written down like this, sine square x, that is same as sine x whole square, which means you first find the ratio of the angle and then take a square of it. This is different than sine x square, which will mean that the square is only on x and not on the entire function. So here, if I have sine 4x, I can write it sine square to the whole power 2 and cos square to the whole power 2. Then applying the formula, identifying this as a square minus b square, it becomes a minus b times a plus b. And this becomes 1, again using that very same trigonometric identity that we use every time. And as far as this is concerned, sine square x minus cos square x, this is going to be my final answer. Though it could be simplified more, I can factorize it more, but this is the form I had to bring it in, so I will stop here. Looking at another example, I have to prove sine 4x minus sine square x identical to cos 4x minus cos square x. And here, since these are equally complicated sides, so it wouldn't matter which side do I start from. If I start with this side, I'm going to try to convert this into cos. Or if I start with this side, I'm going to try and convert this into sine. It's a very random pick, but I've chosen the left hand side and written it down as sine to the power 4x minus sine square x, and I can see I can take sine square x common. And once I do take it common, since I already had it in my mind that I have to replace it by cos, so I would identify or recall this particular identity, and wherever I see sine square written, I'm going to replace that by 1 minus cos square. And plus, guys, it's very, very important that you do note and recognize that this is not same as sine x equals 1 minus cos x. So if you ever do that, that will be considered wrong. That's not an identity. So this identity is only valid if it has a whole square onto it. Somehow replacing this with cos and cos, I can see that this minus cos square x multiplying by this and minus cos square x multiplying with this simplifies to this. And rearranging it gives it exactly into the form that we had to bring it into. Moving on, another example where I have 1 minus cos x times 1 plus 1 over cos x. Very clearly, I have to simplify this by adding fractions. So I will just take down the LCM. It will be cos x plus 1 over cos x. Just like I can factorize into two factors. I can also multiply two factors using the formula a minus b times a plus b. And that becomes 1 minus cos square x. 1 minus cos square x is equal to sine square x. And I can also split, because I have to see what I have to prove. Although it's being simplified a lot, but I have to see that I have to bring it equal to sine x times tan x. So if I have sine square x, that is sine x multiplied by sine x. So a lot of times what we do is driven by what we have to prove. And then this sine x is left alone, and this sine x over cos x simplifies to tan x. And that proves the formula sine x tan x. Moving on, having a look at another example, I have to prove this equals to this. Clearly, this is a more complicated side. I started with this side. I could see a common factor. I took it out. I could see tan square, which I don't really like to see, so I always replace tan by sine over cos. So if tan is sine over cos, so tan square must be sine square over cos square. And then I took an LCM, it becomes cos square x plus sine square x, that simplifies to 1. And sine square x times 1 is sine square x upon cos square x. And sine square x upon cos square x simplifies to tan square x. Let's have a look at another example, and this is also a very good representation of the fact that if I have to simplify this into this, I wouldn't want to have tan squares. And to get rid of these tan squares, what I'm going to do is that this 1 minus tan square is going to become 1 minus sine square over cos square. I have more divisibility signs coming, so I have replaced this by this divisibility sign and 1 plus sine square x over cos square x. One thing that we constantly keep on doing is adding fractions and simplifying them. So this is going to become cos square x minus sine square x over cos square x. And this is going to become cos square x plus sine square x divided by cos square x. Cos square x plus sine square x using the identity would be equal to 1. And then I have flipped it over. Why have I flipped it over? Because there's a divisibility sign. So this 1 on top comes at the bottom, and this cos square x at the bottom goes on top. And then we realize that this and this are cancelling out, and this becomes cos square x minus sine square x. Have a look at another example where we have to prove that 3 minus 6 cos square x divided by sine x minus cos x is identical to this. So we started with the left hand side. I've taken 3 common, and this particular example actually sort of demonstrates a very important situation, that since we are so used to of replacing sine square x by 1 minus cos square x, or cos square x by 1 minus sine square x, or sine square x plus cos square x by 1, so we just do not look at the other alternative as well, and that is if we have 1, we can also replace it by sine square x plus cos square x. So keep your eyes open for that. Even that is something that could be required in a particular situation. So if I replace this 1 by sine square x plus cos square x, and this minus 2 cos square x comes down here, and I will sort of simplify it. This 3 is copied as it is. Cos square x minus 2 cos square x becomes minus cos square x. Again, something like this also gives me an idea that I should be trying to go for factorization. So I did a minus b and a minus b of that. One factor cancels out and it converts into the form that is what you exactly wanted. Now, one last example, and this is an important example in terms of the way that, whenever you're trying to prove an identity, just try and keep one thing in mind. You're not supposed to cross multiply. The process of proving identity is that you start from one side and build that up into the other side. That is what you should be doing in all of these cases. So if I start with this side, you might be able to see that initially I can't see any sort of simplification. I can't take LCM, I can't take common, I can't factorize. So I can't really see if there's any possible way of simplifying it into something any further to bring it into that particular form. So this creates another possible step that we can do, which is that if you see a particular factor that you need to bring in as a proof, so you multiply and divide by that factor. So since I wanted to bring it down to that, and that has a cos x in the numerator, but I don't have cos x in the numerator, so I will multiply and divide by cos x. I can achieve the same thing by multiplying and dividing it by 1 plus sine x as well, because 1 plus sine x is not also there, so I can also initiate my working with that and then simplify it and I'll get that. But somehow I chose to multiply and divide it by cos x, plus one more thing that you have to keep in mind. We have actually brought cos x over here, which was never there, for the purpose of proving it to be equal to this side, and we can only prove it equal to this side if the cos x remains there. So obviously it will be completely pointless if I multiplied it and divided it, and in the next step I may think of cancelling it out or sort of getting rid of it because it is getting cancelled out. That's true, but I have brought it deliberately. So I am gonna leave it aloof, separate. I will not touch it. I will just try and simplify everything else but not touch this cos x. So this cos x is going to be copied down as it is. I'm going to simplify other things. So this cos x and this cos x multiplies to cos square x. I can use the identity, write it down as 1 minus sine square x. Then I can use a factorization formula and split it up into two factors. One factor cancels out, and this comes out to be exactly what you had to prove. So guys, that's pretty much it for this particular video. I will be posting more videos related to the topics of trigonometry. This was only focusing on how to prove the trigonometric identities and what trigonometric formulas you need to be knowing. I will put the link in the description for to download this set of notes and worksheet for this particular topic. And if you do like the video and it was a learning experience for you, I would really appreciate if you would like, subscribe and share it. Thank you so much.